Well, one of the things that I've talked to about with some pretty insanely brilliant people is quantum computing.
Oh, yes.
And this new Google quantum computer that can do essentially the way a quantum computer works, a problem that would take thousands of years for every computer on Earth to solve.
I've read that.
It can solve in a second.
Yeah.
Something that can take more years than you literally can understand. It can be solved in 15 minutes.
Yeah, I read that.
It's insane. And this is where it gets really weird. The way it was explained to me, and we should have to Google how quantum computers work and why people connect them to the multiverse so I don't fuck this up. But the idea is that they're pulling answers from different universes simultaneously. They don't even completely understand how this is working. But the amount of power in computing is incomprehensible.
Yeah.
Like you're only looking at it and there's numbers, you could write all those numbers out, but your brain's not capable of grasping really what's going on. Yeah. And it's probably the biggest breakthrough technologically in human history by a long stretch. And it's all happening without most people even being aware of what the implications are.
I don't even know if it's a YouTube video or somewhere else, but I wound up on this video that was like, world's smartest kid thinks that CERN blew the world up in 2008. All right? You got to invest like 20 minutes into this kid talking about things that are super smart, and it's kind of like to show you he's super smart. You know what I mean? This kid. And his dad's doing the recording, I believe, or a relative, somebody very close to him. And he goes into this whole theory of how he thinks when they collided the electrons, I believe, in the super collider, CERN, that they caused some crazy chain reaction that blew up the universe, but they also they created an atom that weighed too much, and the first 20 minutes is also explaining infinite parallel universes.
Look at what it says there. He claims that CERN destroyed the universe during recent experiments, which has resulted in us living in a nearby parallel universe instead.
You're welcome, Eddie.
You've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's like, explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just like a little bit of that, and then explain many worlds theory.
Yeah, good. This is what I'm here to do. So,
thank you.
You know, an electron, take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position, and, well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. You know, classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere, and from that, you can predict what's going to happen, okay? Quantum mechanics says, no. The electron has a wave function. So there's a wave. You know, sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where things get squirrely with people describing it, right?
Yes.
And that's where they want to go woo-woo on you.
It's an opening to be woo-woo, right? When you say, like, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? You know, that's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is what is called the measurement problem of quantum mechanics. That the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function changes dramatically, suddenly, and unpredictably.
Now, let me ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's a couple of ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning, right? Okay. The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact, okay? So that's a part of quantum mechanics. That's the quantum fact, that there's a discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field, or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it in this case doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up, you measured its spin left, let's say, send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
Something like the Matrix, something that's so immersive that you would forget, right, that you were inside a video game. And so that led me to this idea of the simulation point, which is a kind of technological singularity. But then I started to research things like quantum physics and some of the mysteries around, the observer effect and quantum mechanics. And then I started to look at all the world's religions, and I realized that they're all kind of saying the same thing, which is that there is no physical universe. And so, that led me to the conclusion that we are most likely inside some kind of a computer simulation or a massively multiplayer video game, depending on how you look at it.
But where did that simulation come from if we are inside of it?
Well, that's the big question, right? And there's two versions of simulation theory. And, I teach a class on this at Arizona State University. It's probably the first college-level class about simulation theory, and it kind of pulls in science fiction, religion, philosophy, and technology. But one of the key distinctions I tell my students to make, because it's not talked about a lot with simulation theory, is what I call the NPC versus the RPG versions of simulation theory.
Okay.
Right. So NPC, as you probably know, means non-player characters within video games. So those are the AIs in the video game. The bartenders, the people you're beating up, the opponents, all of that stuff. But basically, they're just code and they're AI. Then there's the RPG version, which is that we are actually doing a role-playing game, right? So you exist outside the game, and then you have a character or avatar inside the game. So it's just like what we would consider an MMORPG today, right? Except with more sophisticated technology. And so in that case, you get a little bit of a different answer than if you talk about an NPC-only type of simulation, right? Because that's just running on a computer, and we're all AI in that case. Now, the two aren't mutually exclusive, right? In a video game like Fortnite or whatever, World of Warcraft, you have NPCs and you have PCs or player characters, right? So you've got both of those things going on. And so depending on how you look at it, you might come to different different answers about who's outside the simulation, which would answer the question of who made the simulation, right?
Yeah.
So in the first case, you basically say that if we can get to the point where we can build these simulations, what I call the simulation point. So I call that a kind of technological singularity. Now, we've heard the term singularity mostly because of AI and super intelligent AI, right? And AI is going to take over the world. But the guy who defined the term was actually a computer scientist who became a science fiction writer named Werner Vinge. In fact, he just passed away like a month ago or something. He was a real pioneer in science fiction and the cyberpunk kind of subgenre or so. And so he said the singularity happens when technology increases exponentially to the point where everything will be different for humans after that point.
The chip itself is very small.
Yeah.
It's like the size of a saltine cracker.
Yeah.
And then this entire mechanism around it is just the insane amount of cooling. Okay. Google's quantum AI founder said the performance gains lends credence to the idea that we live in a multiverse. The idea is that Willow might be communicating with parallel universes to finish calculations faster. What does that mean? The announcement led Google's already high stock price to surge, which isn't that shocking, but perhaps most surprising for us lay people that Google's quantum AI founder and lead Harmut Nevin said that the chip's performance lends credence to the notion that quantum computation occurs in many parallel universes in line with the idea that we live in a multiverse. And then it says, excuse me? This obviously has caused a bit of a stir and it isn't exactly clear on how he made that leap. It sounds a bit like something out of a sci-fi movie, and I'm definitely not going to pretend I'm an expert, but it's worth pointing out that Google is very much still in the theoretical research phase of this journey. This is very weird stuff. It's an exciting look at what computing might take one day, but it isn't something you're going to see in your next Pixel phone. Quantum chips need to be isolated in incredibly specific chambers. Yeah, this is the thing. It has to be cool to a point where it's colder than outer space, sealed away from any possible signals such as microwaves, radiation, radio signals, etc. for fear of that noise leading to potential mistakes, and have specific signals delivered by purpose-built wires. Who figured this out? Where are those eggheads? Jesus
How did
Christ.
they even come up with that if that has to be the case?
How did they figure out that you have to do that?
It's not that we don't know whether the electron is spinning clockwise or counterclockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly not just that we are lacking some knowledge. It's that the knowledge really isn't there. And again, this is how we teach quantum mechanics in textbooks. And then I'm going to correct it because Many Worlds is much better. But This is the standard textbook version. There's a wave function. The wave function for a spin it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, a little piece of uranium, so it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrödinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron. What is its wave function going to do? What is the wave function of the electron going to be? And the answer is it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah, all directions evenly. But you never see that.
Is that roughly
always
based
see a
on the
line.
shape of the piece of uranium? Does it vary?
No, because the electron gets from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. but when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it.
So when you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, me and Einstein think this, right? So Einstein is one of the secret heroes of the book because he has this reputation as someone who just couldn't quite accept quantum mechanics. The title, Something Deeply Hidden, is a quote from Einstein when he was talking about when he was a kid and he had a compass, right? And he was given his first magnetic compass and he could rotate it this way and that way and it always pointed north. And you and I would go, that's cool. But he was Einstein. He's like, wow, this is amazing. Why? How does it know where north is, right? And he said there must be something deeply hidden that explains why it's doing this mysterious thing. And he felt the same way about quantum mechanics, that we gave these set of rules, which are called the Copenhagen interpretation of quantum mechanics. One set of rules for when you're looking at it, one set of rules for when you're not. And Einstein was like, oh, come on. Clearly, this is not the final answer to the nature of reality, right? He wanted to know God's thoughts. He's like, I want to know everything. We're not done yet. There must be more going on. And so many worlds is one of the proposed answers to what could be going on. It's not the only one. There's alternatives, but it's definitely my favorite. It's definitely the easiest one to write down. Let's put it that way.
Okay, so hit us with this many worlds theory.
Okay, so think about this electron. You say that it could be either spin up or spin down. It's a combination of both. That's its wave function. You measure it, you only ever see spin up or spin down. So Copenhagen says that's because the wave function suddenly changed, snapped into place when you observed it. Don't ask me what it means to observe something. That's not what Copenhagen lets you ask.
Okay.
Many world says what you're missing is two things. Number one, you're a quantum system. You're obeying the rules of quantum mechanics. You're made of atoms and electrons and so forth. You have a wave function too, okay? So you're secretly treating yourself as a classical thing when you make that measurement, but you really should be treating yourself quantum mechanically, right? That's one thing. And the other thing is something that Einstein invented, namely called entanglement. When quantum mechanics says there's a wave function for a system, it doesn't say there's a separate wave function for every particle, right? It says that there's only one wave function for the whole universe. So the way I like to say it is, imagine two particles come in and bounce off of each other. Either one has a wave function and it's unpredictable exactly what angle it's going to go off at. So both of the particles that go off, you don't know where they're going. But because momentum is conserved, if they came in at equal velocities, they'll go out at equal velocities and in opposite directions. If you measure one, then you know where the other one is going, right? That's entanglement. The observed state of one system can be related to the observed state of another system.
Well, if there was something they could do, that might open up a door to a parallel universe, you don't think they would do it?
Stranger Things, you mean?
Yeah.
Say that's
this
the goal.
Is Stranger Things. I mean, things are strange, right? It is Stranger Things.
Bizarro world.
You know what's the weirdest one? Is the people that dismiss climate change. That is the weirdest one to me. So I'm like, I'm trying to figure out what's the benefit of dismissing climate change, other than if you work for like the oil industry or something.
Well, Iceland just lost a glacier.
Yeah.
Like they just posted a whole thing of 10 or 80, like something in the 80s, a glacier picture of it, and just now, and it's gone.
But I'm not even saying like blaming anybody for it. I'm saying dismissing it as an issue. I'm like, let's pretend that people have nothing to do with it. I wish people had nothing to do with it.
AI starts to become super intelligent and it grows exponentially and everything will be different. But I think this idea of the simulation point where we can create simulations that are indistinguishable from reality. And I lay out like 10 stages in my book of all the technology we would need, including brain-computer interfaces, like in the Matrix, right? So
or Neuralink.
Right? We're getting there, right?
We're very close.
We're at the beginning of that whole phase. And so that's stage 8, stage 7 and stage 8 on the way to the simulation point. And being able to read but also then being able to write memories as well. And then so the definition of the simulation point is being able to create a virtual reality that is indistinguishable from physical reality with AI characters that are indistinguishable from biological characters. So, you wouldn't be able to tell you're talking to an NPC, basically.
Right.
We're getting closer to that already, right?
Yes.
Yeah, I mean, there's like companies out there doing smart NPCs now inside video games.
Right, but what would be the difference between looking at what is possible in the future and making either a hypothesis or suggesting that has already taken place?
Right, so that's kind of the leap, right, that you need to make, which is to say that if we can do it, now let's imagine a civilization that was 1,000,000 years ahead of us, 1,000 years ahead of us.
Yeah.
Even 200 years ahead of us, right? But certainly 1,000 years ahead of us. So where will computers be in 1,000 years? They would already have created these types of simulations.
Right.
Right, because if we can do it, now 50 years ago, we didn't know if we could do it. We didn't know if computers could get to that point. Right? Today, we're pretty sure we can get there. In fact, I'd say that I'm 70% sure that we will get to the simulation point, which means I think there's a 70% chance we're living inside a simulation.